All right. So we're going to look at kind of the anatomy between galvanic, what we also call voltaic, and electrolytic cells. So in any kind of battery or cell, we have an anode and cathode. Those are dependent upon what type of materials are present. So like things like zinc are not always an anode. They're an anode when paired with carbon because carbon is more the cathode. And we'll get to the understanding of how we understand which one to be which. There's also going to be some electrolyte paste of some sort, some kind of way of transmitting ions or charges so we can have a flow of electricity. And then there's some kind of spacing of some sort. So you'll see this picture as we go throughout. So anodes are marked with a negative sign. This is where electrons are being lost. So electrons are traveling from here across over to the cathode, which is positively charged. So it makes sense that it's attracting negatively charged electrons. They leave and flow towards the cathode. Cathode, positively charged. Electrons are being gained. They're coming from the anode. We can also see some of the solutions in here. We can see that we not only need the metal, but we need to have a solution containing metal ions of the same sort. Again, even on the cathode, metal ions of the same sort of the metal of the cathode. A little different atomic view. Again, using zinc and copper. Zinc and copper is like the go-to for these type of things. So, anode loses mass as the cell runs. The metal electrode has 2 electrons lost by each zinc atom, so they become zinc atoms into zinc ions. And because they become in the solution, they're no longer the part of the anode any longer. This is where we have oxidation, going from 0 to 2+. On the other side, we have the exact opposite. So we have the idea of the cathode, where it's going to be gaining mass, because we have parts of the ions becoming parts of the metal as they're gaining electrons. We can see that this is reduced to going from a 2 to a 0. There's also a salt bridge containing potassium nitrate. So as charges are lost from the anode side, negative ions are coming in to replace those. As positive charges are being lost on this side, potassium ions are coming over. Again, we get potassium nitrate. It's not going to change anything, but of course the nitrate is going to be part of the zinc. So this is happening at the atomic level. And again, most likely not going to view this on the AP test, but you need to be able to explain it. So this has a good description of what's occurring at the atomic level. Now there's a lot of different types of, what do you want to call it, mnemonics to help you remember what's going on. So a red cat, reduced cation, gains what an ox loses. So all of this is looking at trying to keep straight what's going on with what. Anode oxidizes, reduction at the cathode. Anion flow goes in a circuit, a cycle. So of course, if the electrons are going from the anode to the cathode, some kind of anion is going to need to flow in order to balance the charges. Again, anode is the electrode where oxidation occurs, and ox, cathode, red cat, electrode where the reduction occurs, red cat. Very simple to get confused, very easy points as well, which often will come up somewhere on the AP exam. So, there needs to be a salt bridge in order to balance the charges. Anodes making new cations, losing electrons, so the anodes enter from the salt bridge to balance. Cathode losing cations from solution. From solution. So cations enter from the salt bridge to balance the loss. Again, potassium's not going to do any bonding with the copper, and because the other anion's nitrate, nothing's going to be occurring. So we can see that there's a constant change in the solutions that are found because they're either increasing in concentration at the anode, or decreasing in concentration at the cathode. So keep that in mind. Balance of, what's the conservation of mass at work? So we say that the salt bridge completes the circuit and maintains charge balance. Okay, without it, you don't get a flow of electricity. With it, you do. And if we didn't have something else in here, then we wouldn't have the circuit occur. Now, here's a quick summary. I'll let you just kind of read it and what's going on. We have been talking about a voltaic cell. This is an electrolytic cell, so that uses electricity, generally from a battery, in order to drive a reaction. We'll see about those a little bit later, but this is the idea of what's going on in an electrolytic cell compared to a voltaic cell. Similar down here. Difference is with an electrolytic, you're using a battery. You're not generating voltage. You're using voltage in order to essentially move mass around. So there's some notations that you come across. There's cell notation. You also call it line notation. It's a shorthand. So we have the electrode first and the electrolyte. We always put the oxidation half first. Then the electrolyte and the electrode. Reduction half second. So you can see that the electrolyte is kind of written as such with the kind of salt bridge in between. You see that similar to here, anode, salt bridge, so like anode, solution, salt bridge, solution, cathode. So it's kind of the same setup of what you'd see in a generic regular cell. This just means it's a phase barrier between the difference of a solid and an aqueous solution. If you had multiple, a comma is used rather than that. That'd be something like if you had something in a sulfuric acid and potassium nitrate or something in order for the ions to balance. Those would use often an inert electrode. Sometimes they put concentrations in also, so they'll say like 1 molar or half molar. Just got to be aware of it. You'll see stuff in Pearson. I think you'll see a little bit on AP Classroom, but it's again another way of showing the exact same thing, only in a shorthand, which is what we do all the time concerning chemical equations and shorthand for units. So again, something like this, line notation. We've got the idea of different charges moving around. Anode material, zinc. Anode solution, zinc 2 plus aqueous. Sometimes they'll put the full compound. Sometimes they'll just put the ions that are important. Then we have the cathode solution and cathode material. So again, trying to just give you different variations of what these will look like. Even this one is a different variation of what we saw previously. Some mnemonics. Leo goes grrr. Loss of electrons is oxidation. Gain of electrons is reduction. Oil rig, oxidation is loss of electrons. Reduction is gain of electrons. You just want to keep those in mind. I often will just think of the half reactions. Oxidation goes up. Reduction, of course, goes down. So I'm looking at the charges. And of course, elements are 0. So if you go from an element to a 2 plus, well, that's oxidized. That went up. It didn't reduce. Likewise, if you have 2 plus goes to 0, then it's going to be a reduction because it went down. We're going to see a lot more positive ions rather than negative ions in these cases because we're dealing often with metals, and metals make positive ions. So I don't understand mnemonics all too well just because it doesn't seem that the things are too hard here. It's not like we're doing all the different planets and their moons or something like that. But whatever works for you, let it do. Again, oxidation goes up. We can see that here. As you can see, you're giving off electrons, which makes sense of why these are anodes, because they're releasing electrons. Cathodes, which are positively charged, like these guys here, taking in electrons to make more of the metal. And again, reduction going from a positive charge to 0. Now, a little refresher concerning oxidation numbers. We did this back in the day. I can't remember what unit. I think it's end of unit 4. Tracks how the electrons are. Again, when you think of something gets oxidized, something gets reduced. Remember, these are oxidation numbers, +1, -1. Sometimes they're easy, sometimes they're more complex, especially if they're part of like a polyatomic ion or something. Here's some of the old rules. You can pause it, go through it, review it as see fit. But a lot of them are pretty straightforward. And again, I think we're dealing with most of the regular common stuff. We're not dealing with weird exceptions to the rule. Now, balancing redox reactions. If you did these in college, they're much, much more complicated. You really have to balance the electrons, not just the atoms. Basic steps: assign oxidation numbers to determine which things are oxidized and which are reduced. You might have 3 elements, 4 elements on the left and 4 elements on the right, and you might only have one thing oxidized and one thing reduced, and the other stuff stays all the same. Sometimes you might have a couple things oxidized and a couple things reduced. It really depends. More likely, though, it's just 1 and 1. You'll have an oxidation and reduction have to combine. You're going to need to tell which is which, but it's probably not going to tell you which is which. But it might say this is at the anode, this is at the cathode. So knowing which one's which of anode and cathode. Now what's simple is that you can easily balance the atoms, and then you need to balance the charge by making sure you balance the number of electrons. They're often placed together. We're adding the half reactions back together, simplify and check. So what you'll view if you go online for balancing redox reactions, you'll see really complicated stuff. We're not doing that. I've never seen an example on the AP exam where you're doing all these complicated things. So we're going to go with the shorthand. So watch electrons, charge, and the atoms. So you'll have things that are like 2 half reactions based upon what's being oxidized and what's reduced. Rule to follow: the electrons must cancel when the 2 are added. Another way to say it is the number of electrons in each half reaction must be equal to when the 2 reactions are occurring. What that means is that one or both equations must be multiplied through a factor so things will cancel out. The value is selected so as to make the number of electrons equal. So in the problem that we've got, the top reaction with silver must be multiplied by 2 across. Notice each separate substance is increased by the factor amount. Occasionally, sometimes students will only multiply the electrons by the factor. Everything needs to be multiplied. So then when we add the 2 together, we get kind of this net ionics going on. Again, watch your charges. Don't just drop them, because this is not the same as this. With electrons being canceled out on both sides, we're left with a 2-to-1 ratio. We can double check. We have 2 silver, 1 copper, 1 copper, a 2 plus charge, 2 times 1, and a 2 plus charge. That tells us we're good to go. Another good example, if we have this equation here, what do we really have? Well, I've got my half reaction here and my half reaction here. All the electrons, charge, and atoms need to match, so the simplest is getting the electrons to cancel. I see I'm going to have to multiply this times 2 because I have 2 electrons over here. And I've got my original. Seeing the electrons are cancel when they're quote-unquote coupled. The result will be my given equation here. I can see that the electrons match because I have none left. The charge is 4 plus on either side, not 4 plus. Oh, I'm sorry, it is 4 plus. So even I messed up that. 2 times 2 is 4. 2 times 3 plus is 6. But there's 2 times -1. So 4 on the left, 4 on the right. And I've got 2 iron and 2 iodine. So, they can be a little more complicated. However, this is also just the ways you're going to be going through it because you're going to be doing this with half reactions. So, oxidation reduction recap. Read through this. Take a moment. Kind of just summarizes these ideas going forward. One last little bit. Oxidizing agent, reducing agent. These are terms that are around. You're going to see them quite a bit. However, they're kind of outdated terms. So an oxidizing agent does the oxidizing. It is reduced. So reducing agent becomes oxidized. These types of terms are kind of confusing, and according to the AP College Board, they've eliminated using these terms. However, in talking about them and seeing them, you're going to come across them, so I wanted you to be aware of what they stand for. Now, I said we'll get to electrochemical cells, and here we are. So electrochemical cells, we have the reverse. Oxidation occurs at the anode, reduction occurs at the cathode. This is the reverse of a voltaic cell. A voltaic cell has anode with the electrons, cathode with the positive charge. And this would flow and create in a successful cell, a voltage. In an electrolytic cell, though, electrons are drawn off the anode, so it must have a place to release the electrons, the positive terminal of the battery. Electrons are forced towards the anode, so it must have a source of electrons, the negative terminal of the battery. So if it's got a battery, boom, electrolytic. If it has often what's called a voltmeter, that is meant to measure the amount of volts in a voltaic cell. Oh, got that one again. There we go. So voltaic cell, you can see you got the voltmeter. Electrolytic cell, you've got the battery. Again, this is the anode because that's the source of electrons. Those are drawn to the positive end, right? Negatives are drawn to positive. This is the source of electrons in the battery. That's going to be attracted by the cathode, which is positively charged. You can see at the anode, you have an oxidation and you have a reduction of the cathode in electrolytic. Everything's just reversed because, again, the flow of electrons is reversed. So, again, summary to have here, this is not spontaneous. This, of course, is spontaneous. You have a positive cell potential, as we'll get to calculating those. This one has a negative cell potential. So, again, we use these all the time. That's why it's going to be important to know the difference. And I believe that's it for this section. Next, we're going to be looking at calculating these. So come in with your questions, and I'll talk to you later. Take care.